The next task is to generate the shellcode. To do it, first of all, start the Metasploit. Send the Metasploit and start the Metasploit console. It will take a while, the first starting. The Metasploit is started. As you can see in this version, I have 340 payloads, and I want to choose a nice payload for myself. First of all, I use the help command. This is the most important one. And if you look around, you will find a show, which prints you some information about modules or payloads. So I will use the show up. The backspace is not working. It often happens in Metasploit. The backspace doesn't work for the first one. In reality, it is working because if you type something here and you use the backspace, it deletes, because if you hit the enter, there is nothing. If I write some W, I press one time the backslash, then it's really deleted, just you are not able to see it. It will work correctly after 3 or 4 restarts, but now I don't want to restart it so many times. So I will use the show payloads command, and it will print me every payload, and I choose a nice one. For example, now I will use a simple one, the Windows/exets payload. It's here, Windows/exets. It will execute an arbitrary command under Windows. So I can go to the context of it by the use, and after that the name. So Windows/exets. I copied it, so I just paste it here. And I'm within the context of it. And the next thing is to check the parameters. It can be done by the show options. This command print me the parameters. And as you can see, this exets payload has 2 parameters. The first one, and it is a required one, is the cmd, the command what I want to run. I can set it by the set cmd, and here the command I will start the evil calculator charts.exe, and it's set. The other parameter is the so-called exit function. It's about the following thing. You will insert here your shellcode or your payload, and it will run. So it will have some end. If you just don't generate any end of it, then it will continue to run, and as you can see, the application will freeze. And the question is that what kind of end Metasploit should generate here. For example, it can generate an end of the application of your shellcode to close the process. It will be fine for me, this is the process. Or thread to close the current thread. For example, in case of a multi-thread application, you attack the application and you fire your shellcode, and when your shellcode is finished, you just close your thread, because then the application will continue to run. The administrator will not recognize it, which is much less sensible, and this is how it can work. Of course, there is an option like none. For example, if you create a Trojan horse, then you want to write the end of it manually because you insert it to some other application, other code, and you have to, for example, do some stack adjustment or jump back to a correct position, setting of some registers maybe, or restoring some registers. It depends on the situation. So it cannot be done generally in those cases. And there is the SHEC, that's the structured exception handler. It's widely used in Windows environment because there is a defense mechanism against this kind of simple buffer overflow attack. In that case, they add here some so-called stack cookie. I will add it here. And if this stack, and before the return, they will examine this value here, this stack cookie value, and if it is modified, then the application will just exit without running any further code. But now we don't have any stack cookie here, so it's just another possibility. Okay, so let's generate our shellcode. So I set both the parameters. Let's check if it is really set. I use the show options parameter, it's here. Oh, one more thing what I forgot to mention. If you use the set command, you can write the name of the parameter in any cases, so the CMD is exactly the same. But the set CMD, so both of them can be used. But I recommend you to use it with correct case settings, because in those cases the tab is working. So if you type here capital C or capital CM and tab, then it will add you the necessary character. Okay. So as you can see, I set the calculator and the exit function, and now we can use the help command, and we are able to see there is a generate command which generates the payload. Okay, let's try it. Let's try to generate it. And it generated a payload. It has some problems. First of all, if you take a look at it, it is in C syntax. So for example, there are plus signs at the end of the line. But I started to write my exploit in Perl, so I will prefer the Perl syntax. And the other problem, this shell code is full of 0 or null bytes. Here, for example, here one more, and maybe on some other places there are even more nulls. So this shell code cannot be used by me. What we can do, if you use the generate -h command, it will print you the help of the generate command, and it has two switches, also more exactly three what I want to mention. One of them is the -t. This is the output format, and as you can see, we're able to add here the Perl format. Another switch is the -b, where you can add the list of prohibited characters. But I won't use it because now I have a command prompt, and in case of a command prompt, practically the alphanumeric characters are the best to use. Maybe some others can be accepted as well, but you are on the safe side if you strict to the alphanumeric characters. So instead of adding every non-alphanumeric characters to a list, which is a bit too much, I will use the so-called encoder modules. The encoder is practically will generate you a self-encoding application at the beginning of the code, so it will be something like that. There will be a small header of the application, and the small header will extract the remaining part of the application. So here is the header, and it contains some code which is able to extract the remaining part of the application to correct form, and it can be done on the way this application or this whole code contains only some special character set characters, for example only alphanumeric characters. Of course, the main difficult thing here is to write the encoder module on the way. So this is the encoder, also more exactly the decoder module. So the difficulty is here to write the decoder module on the way. It should not contain any prohibited character as well, or more exactly it should contain only the characters allowed by that encoder. And it's a bit more difficult, but it is done, so we don't have to bother with it. So I will use the encoder. Oh, and one more thing, in reality the -b switch also uses only the encoder modules. Practically the -b starts with the first encoder, it encodes your payload, and it will examine if there is any prohibited character. If yes, then it will use the second encoder, and so on, until it will find an encoded version which doesn't contain any of the prohibited characters. So let's try to check what kind of encoders we have. It can be done by the show encoders command, and I have a lot of encoders. What I will want to use is some alphanumeric, and here is this x86 alpha mixed encoder, and I will use this one. So I will use the generate -e, and here comes the name of my encoder. That's the x86 alpha mixed, and after that -t, and I want to get the code in Perl syntax. So generate minus small e x86/alpha underline mixed space minus t pl. That's the perl. Enter, and I got some shellcode. It's here. I will copy it from here. I will copy also the comment, otherwise I won't remember, for example, the size of it. I copied it. And I generate a new perl file, not a pod. It will be the q4.perl. Yes, and paste here my shellcode. And let's write my exploit. It will be something like print. And I want to print out this $buff variable. But unfortunately, as you see, it is only 511 bytes. But I need 1028 bytes. 1028 bytes. So how to make 1028 byte from 511? The answer is you should use some NOPs. Because the NOP instruction is the no operation instruction, practically it is waiting for 1 clock cycle. The CPU will wait 1 clock cycle. And why we use it? Because it does not change any register or any flag or any whatever, so practically it is a safe instruction. You are able to add as many of them as you want. And another advantage of it is that it is a 1 byte instruction. So if you jump not to an exact position, but because of some reasons this position is moving a bit, then you are not able to jump to a middle of an instruction. Because if you, for example, jump to a middle of the instruction, it's a problem because you are not able to interpret the half of an instruction. Most probably you will get just some garbage and the application will freeze. So I have to add some knobs. The question is how to add the knobs. Now I can add the knobs on different ways. For example, I can put my shellcode here to the bottom, and after my shellcode I can add some knobs. So for example on this way. The red one is the shellcode, the green one is my knobs. Or I can do the following. I will add my knobs here at the bottom, and after that I will write, or I will add my shellcode here. Or the third solution, of course, is that I will add some knob here, then comes my shellcode, and after that add some knob as well here. So you have to choose from these 3 solutions one. The question which one to choose. The advantage if you add some knobs to the beginning, so for example if you use this solution or this solution, is that you will have here some space, and you don't have to jump exactly, but it's enough for you if you arrive somewhere to this space. And when you arrive to this space somewhere, anywhere, then you will be able to run your code, because we will use 1 byte NOP instructions. So practically it is a NOP sled. So on this NOP sleds you are able to run exactly to a position and run your code. Practically it will makes your shellcode a bit more stable. Another advantage of adding some knobs here is that you have some space here, what later can be useful, because when you start to write your exploit, most probably you will have problems, because there are problems always. And your shellcode starts to run, but it requires some registry settings, or you have to adjust the ESP pointer because something happens, and things like that. And if you leave here some space, then you are able to add here instructions later, and you don't have to restart the whole work only because of a small problem that can be corrected by 1 or 2 instructions. So it is now quite clear that you have to add some knobs to the beginning. What about the end? So this part. Do I need any knob here or not? The question is good, it depends on the situation. Now, for me, it is very much required to add there some knobs. Why? It is required because my ESP, as you remember, is here when the application jumps to my shellcode and my code starts to run. And the ESP is here and my code is here. So my code starts to run from here to this direction, and of course it is only a code because it's a program code. What else? And every program code uses the stack because of some local variables. So my code starts to run in this direction and it starts to use the stack on this direction. And I guess you can see the problem now. My code runs this direction and it starts to use the stack here, and maybe it can overwrite itself to the S of it can be overwritten. So that's why we have to add some knobs after the shellcode as well in this situation again. Maybe in a different situation you don't have to do it, but now it is required. Okay? So we know that we want to add the knob instruction, and the knob instruction is nothing else but the 0x90 instruction. This is the knob. And we know that we want altogether 1028 bytes, and we have 511 byte shellcode. And if I use my calculator, 1028 minus, if you check it, it's really 511 bytes. 511 equal, oh, sorry, I was in hexadecimal. So again, 1028 minus 511, 517. So I will need altogether 517 bytes, and I have to divide this 517 bytes to two parts, add some here and some here. How you divide it, it just depends on you. You can divide it whatever way you want. Now I will divide it on the following way. I will add here at the beginning, for example, 17 knobs. I will use the 17 because I like the nice round numbers, and in this way to the other side only 500 is needed, which is a nice round number. So here comes my shellcode. It will be 511 bytes. 511 bytes. And after that comes the remaining 500 bytes. So it will be 500. And after that the memory address. So let's try to do it in this way. I come back here. And I mentioned to the beginning I will add knobs \x90 and exactly 17 pieces. And after that comes the shellcode. After that coming the \x90, the knobs again, and in this case 500. Oh, sorry. And finally comes my memory address. That's the \x30, \xf9, \x12, and semicolon to the end. I will check it. 30 F912, yes, exactly. And I save it. And run it. q4.perl. I check the result. There are some characters at the beginning. A lot more same character at the end. So it looks like good. At the end there is something which looks like a memory address, some garbage. And here is a huge mess. Here, that's most probably my shellcode. So from the first sight it seems to be good. I redirect it to w4.txt file. I open this w4.txt file. Here you have to be careful because the Windows Notepad does not show you the knobs, but those are there. So if you start to press, for example, the right arrow, then your cursor does not start to move now. there, still there. But suddenly it starts to move. So be careful to select everything with the select all command, otherwise you maybe lose some characters. And Ctrl-C it, use the buff 1024.exe, paste it here. Again, you don't have to worry about the changing of the representation because only the ASCII code is important and it's only a representation, what you see here. And if you press the enter, the application is frozen. If I go back to my event viewer and refresh, then I can see the result. The application was frozen at the 12 F9 79 position. What happened here? Where is this 12 F9 79 position? If I come back here at the bottom there is the 12 F9 30, and as you remember I added 17 bytes knobs here, so practically my shell code starts at the 12 F9 41 position. And if you check those numbers, the F9 79 is very close to this F9 41, so this application was frozen somewhere close to the beginning. So it was frozen somewhere here, let's say. What happened? Why it was frozen here? Most probably it is frozen so close to the beginning, then there is some problem with the encoder. Maybe after the encoding, the decoding was not correct, and immediately after the decoding module, the application was frozen because the wrong decoding, it was just some garbage. And really, this happened because we used the encoder in a wrong way, this alphanumeric encoder in a wrong way. We didn't set up every parameter, and let's try to fix those parameters now. Let's go and find what we did wrong with the encoder. If you go to the C Metasploit, Ops, Pro, MSF3 modules, encoders, and here the x86, and here is the alpha mixed, and you open it, for example with WordPad. I use the WordPad instead of the Notepad because there are Linux line ends and the Notepad doesn't display it correctly, so I use the WordPad. And if I start to go down, you find here there is a decoder something, and you can see here it tries to find some variables. For example, it wants to get some register, it is called buffer register, and it wants to get some offset, it is buffer offset, but I didn't give it. If I don't give it, then theoretically it shouldn't be a problem because it should be able to solve it. Here is the code for that, but it is not good, so it is not working. So that's why we have to set this buffer register and buffer offset parameters, and the question is what to set there. You have to use those two parameters to define the beginning position of your shell code, so practically this position, the beginning of the decoder. So more exactly, I have to define this position, it's here. And how I can define it? Now comes that information what I mentioned to remember. You remember that this value is stored in the register EIX register. So practically this position is at EIX, which is here, plus 17, because if you remember I added 17 bytes knob at the beginning. So I have to come back here and set the buffer register set buffer register to AIX. But this instruction is wrong. Please do not use it. Because if you run the set command just alone, you will see that there are two kinds of variables in Metasploit. One of them is the global variables and the other one is the module variables. If you take a look at it, this global is called as data store, and if you recall it, I use the notepad and I come back, it refers to the data store. So you have to set a global variable, not a module one. Please don't mix them. To set a global variable you have many options. I guess the simplest one is to use the setG command. The G there is as global. But you can also use the back command, BATSC command to go out from the context of the payload and set the variable at the root of the Metasploit tree practically. But I think the setG is simpler. So setG buffer register to AIX and setG buffer offset to 17. It's here, and if you run the set command just alone, it will print you there is the buffer offset 17 and buffer register AIX. So I defined this starting position by the help of those two values. Okay, now we can generate our payload again. So we can use the generate -e x86/alpha underline mixed and -t pl, that's the Perl command, and it generates some payload for me. It's now 454 bytes. Of course the size is changed because I used it on a different way. So maybe in this case the size changes. No problem, the size changed. We have to recalculate the number of the knobs. So I just come back to my command prompt and create, not a pod, and it will be the q5.perl script. Yes, I want to create this file. Come to the Metasploit, copy the content of it. You just have to select it, and when you release your left mouse button, it is copied to the clipboard. And I paste it here to the notepad, and I have $buff variable contains my shellcode. Now I use here the print command, and I will have to use knob instructions. And how many knobs? As you remember, those knobs are here at the beginning. And here at the beginning I must use the value 17. Why? Because here in the buffer offset I set the value AIX plus 17. So this 17 for me is fixed. Or if you want to change, of course you can change it, then you have to generate a new payload. So I add here the value 17. After comes my buffer, $buff variable, which contains my shellcode. So I added this one, my shellcode. It's now 454. And after that comes some knobs. It will be not 500, but 1028 minus 17 minus 454. It's 557. So here comes 557 knobs. 557. Okay. So I add here \x90 and altogether 557. And to the end comes my memory. address, that's the \x 30 F912 \x F9 \x12 and semicolon. Save. And let's run it again. q5.perl generates something for me. And let's check it quickly. There is something at the beginning, much from the same character at the end. So most probably those are the knobs. Some garbage at the end which looks like as the memory address. And here is some mess. Maybe this is my shellcode. So it seems to be good. So q5 redirected to w5.perl. I opened the w5.perl, sorry, I wanted to use w5.txt. I opened the w5.txt. Again, be careful because the notepad doesn't show you the knob instructions. So select all, copy, and I paste it after the buffer 1024.exe, run it, and it frozen again. Let's see what happens. If I go to the event viewer and refresh the event viewer, here it is. Now it is frozen at the position 12 FA11. This 12 FA11 somewhere close to the end, because here was the F9, how much was it? 71 if I could remember, or something like that. 79. F179, the previous error was here. Now the error came here, somewhere close to the end, very close to the end. So the situation is much better, but it is still not good. So I have here some problem. What can be the problem here? We found that there is some error close to the end of the shellcode. You are able to debug it instruction by instruction in a debugger, but maybe I hope that you are able to guess. The problem is now that this application of this shellcode is simply overwrites its own end because it starts to use the stack from here. So unfortunately, this 557 bytes here is not enough to store all my local variables on the stack. So we have to do something to solve this problem, and this is why it was good we left here some bytes, those 70 bytes at the beginning, because now we have some places where we are able to fix the problem. And let's try to solve it. So how to solve the problem? The problem is that the ESP is here and it starts to create the local variables here, and unfortunately it will overwrite the end of my shellcode. How to solve this problem? I have to move the ESP somewhere else. It's quite obvious. How I can move? I have many different solutions. For example, I can do the following thing. I can use, as you remember, the stack goes to the lower addresses. So to move ESP to the upper direction, I can use the add command. For example, I can use the add ESP, comma, and some values, something like, for example, add 400 hexadecimal 400 bytes to it. Okay, let's check if it is working or not. Oh, sorry, one more thing. I have to add here the machine code of it. Of course, I don't know by head what is the machine code of this instruction. So I go and open my debugger again and come to the C, only, here is the only debugger. And I open again an application. It is unimportant which application you open because we just want to use the only assembler. You choose here whichever instruction you want and right click and select the assembler or press the space button. And right here, add ESP, 400. And as you can see, in machine code, it is the 81C400040000. It's wrong, because it contains a lot of zeros. So it was a nice idea, but it is not working. So it's not good. Then what we can try? We can try to add a bit smaller number. For example, instead of 400, I will add ESP7. Let's see how it is working. I come back here, choose again some nice instruction and use the add ESP, 7F. Assemble. Oh, it's much nicer. It is 83C4 7F, so the zeros were disappearing, because now I was using a number less than hexadecimal 80. So that's the 7F is the maximum what I can use practically. Then it was interpreted as a 1 byte instruction. I can use a 1 byte add instruction more exactly. As you can see, instead of the 81, it is now 83. And because it is a 1 byte add, not a 4 byte add, that's why there are no zeros now. So it can be a possible solution. My problem with this one is that I don't know how many times use it. So for example, is it enough to add 7F, or I have to use it 2 times, 3 times, who knows? So it is a possible solution, but not a really nice one. Much better solution if you do the following thing. The problem is now ESP is here at the top. So ESP is here. And ESP goes to this direction. And my code starts here, and my code runs to this direction, and that's why there is a collision. What to do? If I were able to move the ESP from here at the top to here at the bottom, then the local variables will go in this direction, and my code will run in that direction, so those two were never able to collide again. So it is much better to move down the ESP than to move it up. Okay, how to move it down? Instead of the add ESP, one can try the sub instruction. So for example, sub ESP, and I have to subtract the 1033 in hexadecimal, that's 408. Maybe you can guess it will not work. If you choose here some instructions, for example this one, and I write here sub ESP and 408, the same things happen like in case of the add, because it is a 4 byte parameter instruction, so it requires a 4 byte parameter. It has to be filled with zeros, so there are a lot of 0 bytes. More exactly, that's a lot of is 2 now. Even 1 is too much for me, so it's not a good solution. What can I do? Like previously, one can guess it, like previously, in case of the add, you can use the negative values as well, and you can use, for example, the sub ESP 7F instruction. Okay, let's try to do it. First of all, sub ESP 7F, and this is the 83EC7F. Okay. Unfortunately, I have to subtract altogether 1032, so 408 in hexadecimal, but I'm able to do only 7F in one step. So I calculate how many times this instruction must be repeated. I come here and I have here 408 divided by 7f equal 8. So I have to repeat this instruction 8 times, or more exactly 9 times, because there is some roundings. But anyhow, even 8 times, this is a 3-byte instruction, as you remember, because it's 1, 2, 3 bytes. It's altogether 24 bytes. It's a bit much for me, because I have here only 17 bytes to solve my problem. Of course, you can do some better assembly programming and create some cycles or whatever, but that's difficult. So it doesn't work. So then what to do? What I want to do is to move the ESP from here to the bottom. Now maybe it came to your mind, the EIX register contains exactly the value what we need. So we can solve the problem with the following instruction: move ESP, EIX. That's much nicer because you can do the whole stuff in one instruction. Let's see how does it look like. I find here some empty space. Right here the move ESP, EIX. And as you can see, it is a nice 2-byte instruction, 8B E0. It's very nice, it can be used, but I doesn't really like this instruction. Why I doesn't really like this instruction? Because this 8B and what else was it? E0. This E0 is a high number, it's somewhere very high up in the ASCII table, somewhere around here. If I could remember, this is the omega or sigma or something like that. So I'm not 100% sure if it can be printed or not, so it is not an alphanumeric character. The 8B is also some high character, so maybe it's not the best to use it. Previously I wanted to use some printable characters, so try to find a solution on the way it contains only printable characters, alphanumeric characters. How to do it? I want to move the value of the EIX to the ESP, but without the move instruction. How to do it? I can use a very simple and usual trick in assembly, that's the push AIX pop ESP instruction pair. I put EIX to the stack and immediately pop it to ESP, so it's practically a move, just in a different way. Let's see how it looks like. I choose here some nice instruction again. I write here push AIX pop ESP. And the value is 50 and 5C. I come back to my drawing and right here this is the 50 and the other one is the 5C. If you take a look at your ASCII table, hexa 50, this is the capital P, very nice. 5C, that's the backslash. Now in the command prompt it can be used because I have no problem with the backslash. Many times the backslash is a forbidden character as well, because it used to be some escaping character and things like that. But now we are lucky, so most probably it is working. So 55C is the final solution now. Of course you can find a better one if you want, but it is enough for me. So let's try to do it. I just copy the previous one, it was the q5.pl, and copy it as q6.pl. And use the notepad to open the q6.perl. And let's see what do I have to change. I have here those 17 knobs. Instead of the 17 knobs, I will write only 15, because I will write here my push pop. That's the \x50 \x5c. So this is how my code looks like now, and I save it. File, save, x. And I run this q6.perl, generates me something. Here is something, and then there are a lot more from those. Letter, there is the p backslash. Very nice. Most probably this is my shellcode. And at the end there is the memory address. So by I it seems to be good. So let's run it. q6.perl. Redirect the output to the v6.txt. Open the w6.txt. Select all. Ctrl C. Close it. And open the buffer 1024.exe and add it as an argument. Press the enter and it now works. So really, it's working. So finally, he was able to write a working exploit to this sample application. Of course, you can add some more correction to this exploit. I close it and reopen it. For example, there is one more problem with this code, or one more not so nice thing, let's say that, because it is working, so there is no problem. That not so nice thing is the following. I use here some alphanumeric input. I try to find here some alphanumeric as well. It's okay, the backslash is not really alphanumeric, but okay, let's accept it now. But I have here the memory address, which is definitely not alphanumeric. It contains, for example, 30, F9. Okay, the 30 is good, but the F9 and 12, those are not good values. How to solve this problem? So, for example, to try to jump somehow to my shell code, but into the memory address, I want to write some alphanumeric values. The problem is that, as you remember, we wrote here the address of this position, because here is my code. So I want to arrive here, so I have to write here that value. But now I'm not allowed. Then what to do? The solution is the following. I can do some indirect calling of my code. For example, anywhere on the memory, as you remember, the EIX register points to this position. Let's try to use somehow this fact. For example, if you find anywhere in the memory a jump EIX instruction, and you write here the address, so instead of the old EIP, the address of this jump EIX, then what happens? My application will return to this jump EIX code, and because it is a jump EIX, it will immediately come here. So I can jump back indirectly. And why it is good for me? It is good for me because I can search for this jump EIX anywhere in the memory, and maybe I can find such an instruction at a position, at a memory position, which contains only printable characters. It can happen. Let's see if it happens. First of all, what I'm going to do is to go to the View menu and find the executable modules. And here you see that the buffer 1024.exe uses 3 DLLs. And if you take a look at those DLLs, one of them is very promising, and that one is the crtdll.dll, because it starts with the value 6D. If you take a look at the ASCII table, and 6D is nothing else but the small m. It is a printable character. If you take a look at the second character, that's the 57. If you take a look again to your ASCII table, the 57 here is the capital W. So the beginning of it is printable. So hopefully, if you can find within this module some jump EIX instruction, it will be good for you. Oh, one more thing. This jump is, let's say, that jump equivalent, because not only the jump itself is good for you, but for example the call EIX is good as well, or if you use the push EIX return instruction, two instructions, but good as well. So jump equivalent is the correct expression for this one. Okay, I come back here. The second one is not really good because it contains the B7. And the other one contains the 09. So this is my choice. I come here, double click on it, and you come here, and I search for command and search for jump EIX instruction. Find. Oh, we found one. There is the 5C. That's again the backslash. The backslash strikes back. But we know that it is working for us, so there is no problem. And there is the 27, that's the other value here. If you take a look at it, 27, that's the apostrophe. Again, it can be often a prohibited or bad character, but in our case, in the command prompt, there is no problem with it. But, of course, you can use the Ctrl L to find some other. But as you can see, item not found, so I have no more jump EIX instruction in this code, so I have to turn to the jump equivalent instructions if I want to use a different one. Now I will try this one. I close the Q6 and I copy the Q6.perl as Q7.perl and open it. Notepad Q7perl. And I change this memory address to the new one. It's again, you have to change the byte order to the opposite, so 27 5C. So I come here, backslash x27 backslash x5C backslash x. Come back here, 5860. So 58 backslash x 6d. So this is my input. Save. Try to run it. Q7perl. Let's see. At the beginning there is something. There are much more of the same at the end. Here is the p backslash, dot the push pop. This most probably my shellcode, and at the end there is the apostrophe backslash xm. Then maybe I thought here w, maybe I just mixed it. Yes, it's really the big X. Sorry, it was my fault. So it seems to be good. Let's redirect it to w7.txt and open w7.txt, Ctrl E to select all, Ctrl C to copy it, and use the buffer 1024.exe and paste it after it. Enter, and the calculator starts again. So it's working. We were able to solve the problem by the help of indirect jump. And in this case, even in the memory address, there are only printable characters. Let's say that. Of course, if you want or you have time, you can find some nicer solutions instead of the backslash and apostrophe. It's just a question of time. So, it's working fine. Now our next task is to bypass the dep, because now there were not any defense mechanism. Let's see how we can bypass the dep in this simple situation with this simple sample application.